All right, so here's my BC calculus review. Make sure you check out the AB calculus review because BC obviously has, like a lot of the material that's the same as the AB, so check out that one also. This is going to be the BC specific topics here. So we're going to start with parametric and vector equations. It's probably the biggest one, or one of the big ones. You usually get a parametric or a polar FRQ. And I would say the biggest thing is to remember that the x and the y coordinates are a function of a parameter t. Position is the function, then velocity, you take the derivative, acceleration is the second derivative. If you ever want to find the speed of something, you do the magnitude of the velocity vector. So we use that Pythagorean theorem to find the magnitude of the velocity vector. If you want to find the slope of a tangent line, we kind of use the chain rule. It's a version of chain rule. So dy dx is you do dy dt over dx dt to find like slope of a tangent line, or just taking derivatives in general. And then the other thing you do is arc length, which can also be considered distance traveled, right? Like along a path. So think of the arc length as the same as distance traveled. There's two forms. There's parametric form, where you're taking basically the integral of the speed. If you look at this equation, this is really the speed right here on this guy, right? So this is the speed, and you're integrating the speed, and integrating the speed is the distance traveled, or the arc length. If it's not parameterized, okay, this is not part of parametrics, but if you want to find the arc length for non-parametric form, this is the equation that you use instead. Okay, it's just as a function of x, but it's more common to find arc length by parametric form, just in general. Okay, polar equations. Polar equations are a kind of parametric. You're parameterizing by an angle theta specifically. So you want to know the conversion equations here, right? What are the, y is r sine theta, x is r cosine theta, as well as like x squared plus y squared is r squared, and make sure you can convert between the two if necessary. And then similar, the main thing you need to do is usually not the arc length, but the area equation is the integral of 1/2 r squared d theta between a and b. And I want to just illustrate pictorially what we mean. So suppose I have a function, right, that's f of like r equals f of theta, right? And so what they're telling you is f is like telling you from like there to there, sorry, r is telling you the distance from the origin for this graph, right? And so what is this equation, this 1/2 r squared theta, is you're thinking of rather than slicing things up into little rectangles, you're slicing things up into little arc segments, right? So this is kind of like your d theta, and then this is the area that you're finding here. And so why does it have this 1/2 is because you kind of think of it like an area of a triangle. The area of this triangle would be 1/2 the base times the height, which turns out to be 1/2 r squared d theta. And so the big important thing is when you're bounding the integrals, you're finding the angle bounds on what you're doing to find the entire area. Like this should be angle like A, and then like this angle from here to here would be angle B, and that's what you're integrating. Now, sometimes you need to find the intersection points with the curves to find what those bounds are, if it's like outside or inside a curve. And sometimes you have to do the area of the larger one minus the area of the little one. So you have to do sometimes the integral of 1/2 like r2 squared minus r1 squared d theta to find the area between two curves. But that's the general idea of what you're going to do for that. So the bounds is probably the hardest, or the part that you have to really think about the most is how do you find intersection points? If you have two curves, you set the r's equal to each other and find the theta. They don't do any advanced they don't usually ask you anything very, very complicated when it comes to finding points of intersection for polar curves, even though those can get complicated in general, but the College Board tends not to make that part too difficult. You just have to know how to find the intersection points for fairly simple curves. When you find the slope of a tangent line, it's very similar to the parametric derivatives that we just talked about for slopes, right? Except now your parameter is theta instead of here. And when you're doing the dy d theta, you're always using these equations here, okay? Because these are your parametrics. But what you're doing each time is you're substituting in for r the function, your f of theta, your r equals f of theta. You're plugging that into there and then taking the derivative of these with respect to theta, right? So you think of it as like x and y are functions of just theta, right? Because r is a function of theta, and then you multiply by cosine or sine of theta. Okay, so that's the basic idea for that one. Series test, this is the one that's kind of the lengthiest. You always get usually kind of a series question. Make sure you understand how to run all of the tests. You don't have to be super, It's not like they're going to give you a random series and you got to figure out what test to run necessarily. They will generally either tell you the test or it will be pretty obvious what the tests are. But make sure you know how to run the test, and also make sure you know the conditions for the test. The main one that has the conditions is the integral test, where the function is positive and decreasing, but make sure you know how to run all of these tests. I will note that Calculus BC does not actually require you to know the root test, even though that is one additional test, but these are the list of the tests that you are required to know, or you're expected to know. And I grouped the limit comparison and direct comparison tests. They're pretty similar. Okay, radius and interval of convergence. Make sure you know how to do that. You're pretty much always using the ratio test, setting it less than 1 to find the bounds for the radius of interval of convergence for a series. Then to determine whether the endpoints converge or not, you have to just plug those values into the series and specifically analyze the endpoints to determine whether they converge or not. Usually one of them will be alternating series and the other will not be alternating series when you plug in the endpoints. So one will be an alternating series test and one will be just a whatever test that you can do. But that's the main time you're going to execute one of these tests, is when you're checking the endpoints. If you're asked just to find the radius of convergence, you don't need to check the endpoints. Only if you need to know the interval of convergence and you need to know whether or not those endpoints converge or diverge, that's when you actually have to plug it in and check the endpoints there. Know how to do a Taylor and Maclaurin series. Maclaurin series is just a Taylor series when you're centering it around 0. But here's the general form for a Taylor series. I should have noted that n goes from 0 to infinity. Okay. And then know how to do the error bounds. Most of the time, they ask you alternating series error bounds, so make sure you're very familiar with that one. But they sometimes ask you about the Lagrange error bound. So alternating series error bound is an error bound you can do only if it's an alternating series. And the error bound is just the term after you truncate it, right? So the point of the alternating series is I'm adding up to a point in the series. And then the term after it, if you take the absolute value of that guy is your error bound. So it's actually pretty easy. You just kind of work out the terms. If you truncate it here, the one right after the end of the series, that one is your alternating series error bound. Lagrange error bound is a little bit trickier. That's when you have a Taylor series. It's not necessarily alternating, but the Taylor series comes up to a point and you truncate it. You look at the next term, but you don't evaluate the next term like you do for alternating series. You do this computation. You do the maximum of the nth derivative divided by n plus, like everything else matches the next term in the series, except for this part right here. This has to be the maximum of the nth plus 1 derivative from the point where you centered the series to where you're estimating the value, right? And so you're just looking at the maximum of that next term over the interval from A being where you centered the Taylor series and X being where you're evaluating the Taylor series at, right? So for example, just to be clear, the Taylor series is like where you're going around, and you might be like using like 1.1 if you're trying to estimate what 1.1 is using a Taylor series. Okay. So then you would want to know the maximum of that function from 1 to 1.1. Now, this is just a maximum. That maximum can be as high as you want, just something like that's reasonable and useful. Like you don't want to say the maximum's infinity, then your error bound is infinity, and then that's not very useful. Usually you want to figure out the maximum. It will usually be pretty obvious, so they'll give you a lot of information for you to figure out what that maximum is, but just pick a maximum that you know for sure that n plus 1 derivative is under. Okay? And those are the major topics. There's a few miscellaneous topics, I would say, like make sure you know how to do Euler's method, and I didn't put the Euler's method for estimating a solution to a differential equation, as well as knowing the logistic growth model. And then there's a few, improper integrals and things like that. That's in general, in addition to the AB topics. Those are pretty minor. The ones I listed are the major FRQ topics that you usually have to go through. Okay.